Okay, so in this tutorial, we will talk about straw induction. We'll do 2 examples of straw induction, and then we'll move on to injective, surjective, and bijective. Your quiz on Thursday covers 4.4, 4.5, and 5.1. So that includes straw induction and variations of inductions, but I talked about variations of induction last week, so I'm not gonna do that again. Today we'll just focus on straw induction, injective, surjective, and bijective. And after my last tutorial, we agreed that I will do a review session tonight. So review tonight from 7 p.m. and onwards. I don't know when we're gonna end that, but it's tonight from 7 p.m. Using the same link. So it's still on Zoom. We'll still meet here. If you want to join, you can join. The reason I'm doing that is after last tutorial, I feel like people are really lost. So we'll do a review session. We'll go over more questions. We'll talk about more about induction, injective, surjective, and bijective. And hopefully that's going to be helpful for your quiz. Oh, I forgot to ask, how was your test? The midterm. How was your midterm? It was okay. What about the other? Could that be better? Better than the quizzes? Yeah, okay. Okay, so it's better, I guess. You guys are improving. Hopefully, this coming up quiz is gonna be better as well. Wait. Anyway, let's start today's tutorial. We'll do straw induction first. I talked about the principle last week already, so I'm not gonna go over that again. Here is a first example. I'll give you some time to work on this and we'll take it up. Just let me know if you have any question. Anyone finish the question? What do you want? What do you want now? Anyone finished? Can I take it up? Okay, no one said anything. Stuck at the end but trying. Okay, cool. So for the rest of you, can someone tell me what are my base cases? What do I need to show for base case? Okay, we need to show when n equals to 0 and when n equals to 1. Why do you want to show when n equals to 2? Wait, when n equals to 0, we have a0 equals to 0. And we know that a0 is definitely between 1 and 0. And when n equals to 1, we have a1 equals to 1, which shows that a1 is in between 0 and 1 as well. Okay? To prove 1 implies 2. To prove 1 implies 2, showing base case doesn't show you that a0 implies a1. Okay, this is just saying that a0 is true and a1 is true. If you want to show something implies something, that's when you have induction step. In this case, you just need a0 and a1. I will tell you why later, okay? When we reach induction step, I'll tell you why. Inductive hypothesis. So let's assume that n is in between 0 and 1. For n equals to 1, 2, 3 till k. For some k in natural number, what would our k be in this O's? Do we have any restriction for k? Despite that it has to be a natural number, is there any other restriction? Oh, and should start from 0. Okay. K is greater than or equal to 2. Why is that? Anyone know why? Because I already proved Yeah, k greater than or equal to 2. Okay? Now, induction step. We need to show that A of k plus 1 is in between 1 and 0. Now, A of k plus 1 equals 2. So we have this definition here. You can plug in k plus 1 in there. You'll get 1 over 4. Actually, here I'm just gonna leave a question mark here because we'll go back to that, okay? Times a k squared plus a k minus 1 plus 2. This is by definition. Any questions so far? For this step, how did I get this? Anyone has any question? Is it clear? Basically, I just use a definition here, okay? Now, we know that by IH, we know that AK is in between 0 and 1, and AK minus 1 is in between 0 and 1. Okay, this is by IH. Since we have that, we know that AK squared is gonna be in between this as well. Just square both sides. Okay, but we need to know this whole thing. So let's add those two together. That's gonna give you 0 is less than or equal to AK squared plus AK minus 1, which is less than or equal to 2. Okay, and you need to add 2 to it. So 0 is less than or equal to 2, which is less than or equal to AK squared plus AK minus 1 plus 2, which is less than or equal to 4. Now you need to divide it by 4 because we want 1 over 4 times the whole thing. So that's going to give you 0 is less than or equal to 1 over 4 times AK squared plus AK minus 1 plus 2, which is less than or equal to 1. Okay, so therefore you get AK plus 1 is in between 0 and 1 as required. Therefore, by principle of strong mathematical induction, we have AN is in between 0 and 1 for all non-negative integer n. Okay, any questions so far? Brownie, don't bark. How do I know what to prove for base case? Yes, I'm gonna explain that now. Okay. your base case would be, if you look at the principle, your base case, normally it would be P1. But sometimes it's not P1. Sometimes it's not n equals to 1. It's gonna be the first few terms or first term of what you need to prove. In this case, because you need to prove that for any non-negative n. Okay, non-negative integer n. I think I should forgot to put the integer here. Because you want to prove for any non-negative integer n, which means your n starts with 0. So your n start with 0, 1, 2, 3, 4, and so on. Okay, which means you definitely need to check when n equals to equals to 0. Does that make sense? Why you need to check n equals to 0? So your base case, you check the first term or more terms. But in this case, you need to check n equals to 0 for sure. Why do you need to check n equals to 1? The reason is because this definition here. This definition, it's telling us this equation works only for n greater than or equal to 2. So using this definition, you cannot get a A0 or A1. Does that make sense? If I add extra base case, will I get deducted? I wouldn't do that, but I can't guarantee for the other TAs. So it's better that you do it properly because I'm not marking your quiz. So yeah, I can't guarantee anything because I'm not marking your quiz. Okay. Again, I'm gonna repeat it again. You check the first term. Usually you check the first term, but in this case, you need to check the first two terms because this definition, okay, this equation here, can only give you when n is greater than or equal to 2. So you cannot get A0 or A1 by using this. Because you cannot get A0 or A1 using this, when you reach induction step, you are using this definition. Okay? So since you cannot get A0 or A1 from this, that means using induction here, you can never get A0 implies A1. So you just cannot get this because this equation here, it works only when n is greater than or equal to 2. So you don't have this. Okay, since you don't have A0 implies A1, you need to check both A0 and A1. Also, this step gives you what you need to assume for your inductive hypothesis as well. Okay, because this is the place you are using this definition. This is a place you are using the definition, so whatever your k is depends on this equation here. So my question is, can your k be 1? Well, we know it can definitely be 2, but can it be 1? So if you plug 1 in there, what do you have? Anyone? If you plug 1 here, what do you get? So if you plug in 1 here, you'll get, let's write using another color, A2 equals to 1 over 4, A1 squared plus a0 plus 2. Is this defined? Do we have this? A2 equals to a1 squared plus a0. Do we know a1? Do we know a0? Yes. Okay, so that means your k can be 1. So here, it's actually k greater than or equal to 1. Does that make sense? Because this is a place you're using the definition. Yep, okay, cool, nice. So let's move on to question 2. Again, I'll give you some time to work on this and we'll take it up. Hopefully this time you can do everything yourself. Right, so again, my first question is, what are my base cases? One and two. Okay, exactly. One n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 n 1 Some of you might notice that in this question I defined Pn because I want to show you different ways of writing the induction proof. You can pick either way, but the thing is, in my first example, I didn't define what my Pn is. That's why I never used Pn or pK in my proof. Okay, if you see that for inductive hypothesis, I never ever mentioned Pn or pK. So if you didn't define it, you cannot mention it. Now I defined it so I can use it. But both are okay. Okay. All right. So my inductive hypothesis, I suppose P1 and P2 all the way till pK are true for some k in natural. Remember, you always assume for some k, you never write for all k. Okay, so you write for some k in natural number, and in this case where k is greater than or equal to 2. How do I know that? You'll see later. Now we have induction step. We need to show that ak plus 1 is odd. So let's start with ak plus 1. We know ak plus 1, you can use this definition here. So that equals to 2 times ak plus 3ak minus 1. This is by definition. Okay, and you check what your k would be using this. So we know that it could be k greater than or equal to 3, could be k greater than or equal to 2, so you plug it in. Since if k is 2, you have a3 equals to 3a2 plus 2a1. And you know both a2 and a1. So in this case, k equals to 2 is okay. So that's why you assume k is greater than or equal to 2. And any questions so far? Okay, no question. Now, by IH, we know that AK and AK minus 1 are both odd. So we can write it as AK equals to 2m plus 1 and AK minus 1 equals to 2n plus 1, where my m and n are integers. Okay, because this is where you use the definition. Okay, so whatever your k can be depends on this equation. If you plug in k equals to 2, you'll get a3 equals to 2a2 plus 3a1. So that's okay, you can have k equals to 2. That's why it's greater than or equal to 2, because of this equation. Does that make sense? Anyway, this will give us ak plus 1 equals to 2 times 2m plus 1 plus 3 times 2m plus 1. So that's 4m plus 2 plus 6m plus 3. You can write it as 2 times 2m plus 3n plus 2 plus 1, which is odd. since we know that 2n plus 3n plus 2 is an integer, the minimum possible volume for k here is 2, yes. Because if you put 1 here, okay, if you put 1 here, it's a2 equals to 2a1 plus 3a0. We don't know what a0 is, so it's not defined. So the minimum value to make this equation define for k is 2. Anyway, so we showed that ak plus 1 is odd. Therefore, by principle of strong mathematical induction, Pn is true for all n in natural number. Okay? Yes, because the sequence is n here is natural number, so it starts with 1. Why do we never try to prove for all n in integers? I don't think I ever say it in 102, but in some other courses you could be asked for that. Just not in 102 because we want to make your life easier. Also sometimes you might need to do induction on different variables. So you might have 2 variables and you need to do induction on one first and then another one. Sometimes you might need to do induction both twice. So well, I've never seen that in 102, but it could happen. Yes, Jason. I don't think they know countable yet, Jason. I don't think they know countable, uncountable yet. Yeah, but it works for integers as well. It's just you never say it in 102. Anyway, let's move on to injective, surjective, and bijective. So if we have a function that mapped from A to B, so let's draw this diagram where I used so many times. This diagram. So this is your A, this is your B, and we put some elements in there. Okay, so this is saying that F is injective if for every y in B, so those are my element in B, for every y, for every element in B, there is at most one x in A for which fx equals to y. At most one x in A means that you cannot have more than one x from A mapped to the same element in B. So you cannot have this. Okay? You can only have one map to it. You can have 0 elements from A mapped to it, but you cannot have more than one. So for example, me draw injective. So this would be injective. Okay? Let's draw another one for surjectivity. So for surjectivity, you still have the same thing. Let's say we have A and B. And let's put some element in there. It's surjective if for every y in B. So if you pick any element in B, there is at least one x in A for which f of x equals to y. So if you pick any element in B, you always have some element in A that maps to this element. So every single element in B has to be mapped. So they are all not single, okay? There's someone holding their hands from A. So for example, like this. So in this case, every element in B has something mapped to it. So this is surjective. For bijective, it means that you has to be both injective and surjective. Okay? Let's look at some other definitions. So here are two more definitions of injectivity. Both are really important because you use this definition to prove for injectivity. Okay? So if f is injective, then for every x1, x2 in A, x1 does not equal to x2 implies f of x1 does not equal to f of x2. This is the first definition. The second one, we have for every x1, x2 in A, if your f of x1 equals to f of x2, then you have x1 equals to x2. This one is really important because this is the most commonly used definition when you prove injectivity. So when you prove something is injective, you pick two elements from your domain and you assume that f of x1 equals to f of x2, and you do some algebra in between. If you can show that x1 equals to x2, then your function is injective. For surjectivity, this just means that the image of the function equals to the codomain of the function. So image equals to codomain. And when you prove this, what you need to prove is that you need to prove for all y in B, there exists x in A such that f of x equals to y. Okay, so this is what you need to prove when you show f is surjective. And for bijective, codomain is arbitrary. Codomain is usually given. So when they give you a function, they'll give you the codomain, just like this. Okay. I'm just using A and B as the domain and codomain because it could be anything. Anyway, for bijective, it means that for any y in B, there is exactly one x in A for which f of x equals to 1. So let's say you have something like this. Every element in B has exactly one element from A mapped to it. So let's say something like that. This is bijective. Okay. Now let's look at an example. Give you some time to work on this. But it's not some intrinsic property of a function. Well, it is. For any function, you have to have domain and codomain. It has to be given to you. Or if it's not given, people usually assume that it's all the real numbers. What do you mean could be anything? Not necessarily. It's when you define a function, you define it to be something. If you don't tell us what your domain and codomain are, if the function is not defined. That's true, that's true. Not It's just I would say in calculus, usually they don't tell you what the domain and codomains are. But in every other courses, when you define a function, you have to have both domain, codomain, and how the function is defined, like the expression. So for example, I have the same, let's say we have f1 is from real to real, where my f1 of x equals to x squared, and I have f of 2, and I change the codomain to 0 to infinity. Okay, and I have the same expression, x squared. Those two functions, although they have the same domain and same expression, they are different functions. Okay, the f1 and f2, they are different because they have different codomain. They all yield the same value, that's right, but well, in this case, your f of 1 is not, it's not surjective, but your f of 2 is surjective. They are still different functions. All right, let's try to prove this function is surjective. So what I'm gonna do is that I'm gonna write down what I need to prove. Just give me a second. Okay, so this is what I want to prove. I picked an arbitrary element from my codomain. This y is a codomain y, okay? And I want to show that there exists x in real number such that my f of x equals to y. So this is what I want to show. To do that, I want to do some rough work. So I'm gonna write my rough work in another color. Okay, so my rough work is that I will try to isolate x. Oh, this is x. So this will give us y minus 1 equals to 2 times cube root of x. And that's gonna give you y minus 1 over 2 equals to cube root of x. So x equals to 1 of y minus 1 over 2 cube. So I'm gonna say this is my x. Since my y is a real number, okay, y minus 1 over 2 cube is gonna give me a real number as well. So I can pick my x to be this real number. So here is my formal proof. Let x equals to y minus 1 over 2 cube. Since I know y is a real number, x must be a real number as well. So now I picked a real number, x, and I want to show that this f of x equals to y. So that's going to give us f of x equals to f of y minus 1 over 2 cubed, which equals to 1 plus 2 times the cube root of this. That's 1 plus 2 times y minus 1 over 2, which will give you 1 plus y minus 1, which is y. Okay, so here I show that I can find an x in real number such that my f of x equals to y. So that's showing that my f is surjective. Does that make sense? Yes, okay, cool. So how do we show it's injective? I always think injective is easier because what you need to do is you pick two elements from your domain and you assume that your f of x1 equals to f of x2. All right, this is your first step when you prove injectivity. Now let's put f of x1 and f of x2 in there. So that's going to give you 1 plus 2 times cube root of x1 equals to 1 plus 2 times cube root of x2. And this will give you cube root of x1 equals to cube root of x2. Okay, and that's going to give you, so x1 equals to x2. Okay, so since you showed that for any x1, x2 in real number, f of x1 equals to f of x2 implies x1 equals to x2, the function is injective. And that's the end of the proof. Is this on the YouTube channel too? I'm recording it, so it will be on my YouTube channel. Not yet, but it will be. Okay. Any question? That's the end of the tutorial. Any question? Okay, just a reminder, tonight at 7 p.m. we'll do a review session for your quiz. Move up. Okay, cool. It will be recorded as well. Yeah. Alright, so if you have no question, you can leave now. If you have question, I will stay for a bit more. And for those of you who wanna attend the review session, I will see you guys in an hour. For the rest of you, I will see you guys next week. Good luck on your quiz. No problem. Do you need me to go up a bit more? Bye, Jason.